Okay, let's talk refraction of light for a moment. Refraction is another word for bending of light rays. And the bending of light rays happens when a light ray goes from one substance with one density into another substance with another density. And density isn't necessarily the exact right word to use there. We call it an index of refraction, but it's really how much does it slow down light or does it allow light to speed up? Like how easy is it for light rays to travel through it compared to something else? So let's start with some specifics. In air, air is pretty spread out. There isn't a whole lot in air that gets in the way of light. And so it travels about 3 times 10 to the 8th meters per second. Okay, it's a huge number. Okay, now that's the speed of light in a vacuum, and in air it's just a tiny bit smaller than that. So for all practical purposes, we're just going to assume that air and a vacuum treat light about the same. Okay, but when light goes through water or glass or other substances that really definitely are solids or liquids that kind of slow it down and don't allow it to move as fast, we see a measurable change when it changes from one substance to another, when it hits that boundary. So I want to start by having you visualize this. A picture you could see one light ray and you could expand it and blow it up so that it's actually in a really such a magnified version that you could see the light ray as bigger than just something that's infinitely narrow. So I'm going to draw a light ray coming in kind of like this. Okay, so this is a beam of light that's coming down, but it's like it's a gigantic beam of light. And I guess we would assume this is like a infinitely small cylinder, but we're blowing up so we can see the entire cylinder. Now, as it approaches this boundary between, say, air and flint glass is something that slows light down quite a bit. So as it approaches that, at an angle, this corner of the light ray is going to hit this boundary and slow down before that corner will. It's kind of like, let's say you've been pushing your lawnmower across your driveway that's concrete, and you're pushing on the concrete, which is really easy to do, and then you're pushing into the grass. It's really tall and it slows the lawnmower down a lot. Well, if this corner, this wheel of the lawnmower hits the grass before this one does, then just as it hits that, the edge that touches that grass is going to slow down quite a bit. But the edge that doesn't touch the grass is going to keep going fast, and what it does is it bends the light ray. This wheel moves slower and doesn't make it as far. This one does, and all of a sudden we have it moving at a different direction. Okay, now I exaggerated this obviously just for effect to make it easier to draw, but as the light ray comes in, the corner that hits it first is going to kind of create some friction or some drag and just sort of end up pulling it a little bit into that substance. Okay, now we're not obviously going to draw it this way, but I want you to see the purpose behind it, like the reasoning that's there. So let's take something more realistic, like light that's traveling through some glass. Okay, so here's a little layer of glass, like glass you would say have on a window, and we're going to draw a light ray coming in and striking that glass, and the light ray is obviously going to go through the glass still, but it's striking it at this particular angle. I'm not going to put any numbers in right now. I'm just going to call it theta 1. And remember, we always label these angles with respect to the normal, okay, the perpendicular plane. Well, if that happens, and it's going from air, which we're going to learn about this more in the next video, but the index of refraction is 1, and it's going into flint glass, which slows it down, and the index of refraction is 1.52. When that happens, it goes slower here, and this effect occurs, and it always bends towards the normal. Okay, so all of a sudden, that angle shrinks right there. Okay, so the first angle, the instant angle coming in is pretty wide, and then it gets shrunken down and it goes steeper and gets pulled into that substance essentially. And then it's going to continue at a straight line, basically in that path until it exits. And the cool part is when it exits, it does the same thing in reverse. Now it's going from a slow substance into a faster substance back to one that was just like what it came from. And that angle is going to bend away from the normal, and now it exits at the same angle that it came in at the very beginning. However, it's off a little bit in terms of its position. And so this is going to explain to you certain effects you've seen before. So for example, let's say you've been, sitting in a restaurant, you got a glass of water, and you notice that you have the straw sitting in there. Okay, back when we used to be able to use straws. And you look at it from the side, and all of a sudden it looks like the straw doesn't connect, like it's shifted over a little bit. Well, part of that is the light rays traveling from that straw to your eye don't just go through air. Not only are they traveling through water, but when it changes from water to glass, you get the same effect. Whereas the light ray can move a little bit faster in water than it can in glass, and that edge of the glass slows it down, and everything gets shifted over just a little bit, and that's why we see this effect. Okay. Now I use some terms here. Index of refraction, that's we're going to use the letter N for that. That's something that's basically measured by just about every substance we know of, and you can look this up online pretty easy. Every substance we know of that's been studied, we've studied how light goes through it. Lasers are a pretty easy way to work with that, and there's some physical laws that we're going to address in the next video, but N is going to represent a number like this that represents what it does to light, like how much it slows it down. And you notice if air is 1, every other number is going to be bigger than 1, because every other substance just gets in the way more and slows light down. Okay? Angle of incident, angle of refraction. Okay? And then this one would be the other angle of refraction, but it's equal to this one because it's going right back into the same substance that it was coming from before. Okay? Remember that our angles are always drawn with respect to the normal. We don't worry about drawing these complements down here. It's always the ones with the perpendicular plane. Okay?